kick off. Right, so as I say, this week around, we are doing the Embodied Carbon Calculator demonstration. We're really pleased about this bit of work. It's something which, you know, embodied carbon as a topic has become a lot more relevant over the last 6 months, definitely. You know, we've talked many times about RIBA 2030 and Architects Declare. And, you know, the carbon footprint of materials and materials that go into all kinds of buildings is becoming, you know, of kind of greater importance and focus. And we're constantly having discussions with a whole range of kind of design professionals, but particularly architects. We've talked before about, you know, increasingly software being used, specialist software for analysing buildings. And that's kind of fine when you're in the more, you know, you get further on down the line with the buildings design. But one of the biggest cruxes, which I think meets a lot of designers, and actually, you know, even our team, you know, personally, embodied carbon can be for some quite magical and mystical, and it's difficult to know how you actually pin it down. And particularly during the early design phases, how do you inform, if it's important to you, how do you get feedback as to how your designs are progressing against some kind of benchmark or numbers or, you know, framework to say what I'm doing is a good thing for embodied carbon or what I'm doing is a bad thing for embodied carbon? Just some simple feedback. And we talked to a number of architects and just kind of with our finger on the pulse of what was happening in the market. There's all kinds of things being developed, but there was nothing really sat there to help architects out really at the sketch stage, or even as you go through some of the prelim design stages. So as I say, I always do this, just spend a couple of minutes just describing what our business does. And you know, for newcomers to this webinar, hopefully this will just give you a bit of background. Mesh Energy is an independent energy consultancy practice. Really, we kind of make it our mission to improve intelligent design in the built environment. We're completely independent. You know, we're not backed by any manufacturers. You know, we're not taking backhanders from anybody, but what we do is work as closely as possible with design teams to make sense of sustainability in whatever form that comes in. And that's everything from kind of strategic planning to design to helping on site to commissioning and energy monitoring in some cases. So as I say, you know, we've got a team now approaching 10 people. We cover the UK and we deal with the very small to the very big, homes, businesses, blocks of flats, schools, community projects, all sorts. But first and foremost, we're independent and can bring many decades. I think last time we added up, it was almost a century of experience to your project. So with that said, before we actually get into the demonstration, you know, we're quite keen to kind of share information where we can do as a practice. And it's important to know what else is going out there as far as calculators. I don't know if any of you guys are aware of Hawkins Brown as an architect practice. They're quite a big one. Certainly Field and Clegg Bradley Studios are. And Hawkins Brown have come up with a embodied energy calculator, but you need Revit to use it. So essentially they've developed this with a university, and it's kind of like a Revit add-on. Which is great if you've got Revit, but if you haven't got Revit and you don't know how to drive kind of complex software, that can be a bit of a problem. But Hawkins Brown, this one's free from Hawkins Brown, and we're going to share this presentation so you can obviously get access to the links, but you can Google any of these things. So Hawkins Brown have done one, a kind of a snazzy one. There's this thing called Building Transparency. I think this was out in DZ magazine beginning of the year, and a whole load of people have come together to try and develop this embodied energy calculator for the built environment. Honestly, when I saw this, I was like, that's amazing. You know, is there anything that we can learn from this? I looked at it and even I was utterly confused and bamboozled by what they'd come up with. It was very complicated, certainly at first glance. As I say, I've been speaking recently with Joe Jack, I think Joe Jack Williams at Field and Clegg Bradley Studios, and they gave us actually the idea for an Excel calculator. They've been spending months and months developing an Excel calculator, which seems to have some kind of good graphics, but I haven't seen it yet. We did offer to develop that with them, but as of yet, I haven't seen anything. So we just kind of, in the end, we kind of got a bit bored and just decided to do our own thing to help you guys out. But those are some of the names associated with free calculators, embodied carbon calculators, and things to kind of keep an eye on. So the demo that I'm going to do for you on this calculator that we've got is based around a case study actually that we showed last week. We were doing the part 2 of our kind of no added cost and showing how low energy buildings don't need to cost the earth, as the saying goes, and for a small extra premium you can make very, very radical energy savings and carbon reductions in a building. So I'm going to use the same case study, and what I don't want to do, don't get me wrong here, I don't want to get lost in the detail of, you know, thermal bridging and exactly, you know, to the nearest square centimetre how this building was constructed. I don't want to get lost in that, but we're using this as a kind of a real project that we can use. This was a SIPS construction. It had a reinforced concrete raft. It was almost passive house. It's not accredited passive house, but it used an MBC timber frame system, which kind of provides all kind of guarantees, and had an amazing air infiltration rate. And so we will use the dimensions and the structure of this building in the first instance to put into our calculator, and I'll show you some of the other things as well. So this is what we're kind of basing some of our numbers on. So the calculator, what I'm going to do, I'm going to stop the share here, and I'm going to share my other screen. So bear with me. Right, let's just do this. Right, we'll get there in the end. Okay. Sorry guys, I'll just get this up on the other screen. Right, can you guys see the, Rhiannon, can you just confirm that you guys can see the calculator there? Rhiannon?
Yep, you can see it. Right,
okay, fine. Okay, so, right, we'll get there. Okay, so the calculator, as I say, will take you through the basics here, and then get into the actual calculation. So we've got 3 tabs to the calculator. The first one is just as it's entitled, Read Me First. It's just an introduction to the calculator, just takes you through some basic points. And what we've actually got down here is a YouTube link to a really quick kind of 5-10 minute video, lightning fast through the calculator. So we've done a really kind of short explainer video, and you can click on that link and that will take you to YouTube. But first and foremost, if we just kind of go through some of the points here, as I say, this calculator is to help you at the kind of the early stages. It's by no means a kind of a detailed, all singing, all dancing, you know, building physics modeling package. But the tool does use, as a business, we use One-Click LCA, which is a very, very, very well-known, you know, professional software that draws on thousands and thousands and thousands of EPD certificates, which essentially are fundamental for embodied carbon quantification. And what we've done is worked back from that software, taking the real data that software punches out and putting it into Excel. So we haven't just made up the figures in here, it comes from One-Click LCA software. And one of the other things, as I'll go on to explain, is if you're interested in the RIBA 2030 targets, it's worth bearing in mind that you need to take into consideration the building services like heat pumps or PV or mechanical ventilation, heat recovery, in order to make sure that you're getting realistic RIBA 2030 embodied carbon output out of it. But I'll cover that shortly. So there are some simple steps. Essentially, you go through the calculator, fill in the materials, pick your materials, choose thicknesses, you know, pick how many doors, put in the area of those materials. It's pretty basic in that sense. It works on volumes and areas and thicknesses. Then you go in and select what building technologies you want, if you want to get these RIBA 2030 targets out of it. And then at the end, you are shown the relative embodied carbon, both against the RIBA 2030 targets and kind of in clusters, like how much is in the floor, how much is in the vertical facades, how much is in the roof, etc., etc. The really key thing to understand here is color means something. So the yellow cells in the spreadsheet are cells you put information in, and the blue is output. I mean, I've locked down this spreadsheet so you can't type in anything where you're not allowed to, other than this front sheet. This front sheet's completely unprotected, but the other sheets, if you're able to type something, then it's okay to type something in that cell. If you're not allowed to, you simply won't be able to type anything at all. And we've also got the ability to compare models. So you can put in information against a building and then do something a bit different to compare like for like, side by side, and then do something in the third one and say that would be obvious. So if you're interested in RIBA 2030, both embodied carbon and operational energy, you have to realize that operational energy, you have to realize that they're related. You can't just go through and choose amazingly low carbon building materials and, you know, happy days, you've ticked that box in the RIBA 2030, you know, kind of framework or targets. When you reduce embodied carbon to get to the RIBA 2030 targets, your operational energy targets get tighter. So your U values get lower. You will have to put in renewable technology, and the best way, without complicating this, just see that you guys can see that middle tab, okay? Rhiannon, can you just confirm that? It's just saying screen sharing paused.
Which tab are we looking at?
The one that's just come up with the table.
Nope.
For some reason, it's saying the screen sharing has been paused. Let me try that again. Sorry, technical issues at this end. Right, let's try this again. Right, so you should be able to see there a simple table.
Yep.
And this is our middle tab, RIBA 2030. So, as I say, if you're interested in hitting any embodied carbon target, use this table as a reference for U values and the technologies that you should be considering for the calculator. So we've used this table before, and we've used this on real projects, so we know that these U values are pretty good to rely on. So, for example, as you go through the RIBA targets, your walls have to get tighter. If you're trying to hit the 2030 target, your U values for walls have to be at 0.1, roofs around 0.1, floors around 0.1. So, and you've got heat pumps and mechanical ventilation, heat recovery, and solar on the roof. You must drop these things in to make sure you get a realistic embodied carbon calculation. As you start dropping in these other renewable technologies, it will increase your embodied carbon. So it's it's important that you're dropping in the right technologies for the type of target that you're trying to hit. So enough said about that. Let's talk about the calculator. And what I would say is we'll run through this, and at the end we're going to share with you a link where you can download this for free. So keep your eye on the little chat box that we've got that you can use for this webinar. And Rhiannon's going to share that link at the end. So we'll run through this, then we'll run through questions, and then we can share that link. So this is the tab. This is the doing tab. Once you've done lots of reading, this is your doing tab. And as I say, it's a fine balance between getting enough detail in there and making it simple to use. And hopefully we found that balance. We did a first version of this, got some great feedback from about 4 or 5 practices, and this is the second iteration. So at the top here, you can fill in your building name. So, for example, you can type in, whatever your building name is. And as you scroll across, you've got number 2 and you've got number 3 that you can punch information into. So you can call the building name something meaningful, or whether you call it, building regulations, or, whatever you fancy. So you can compare these. So you can type in the title of the building. And as you work down here, although there looks like there's lots of cells, it's actually broken down into the main building elements. So you can have 2 different types of external roof construction. You can have 2 different types of external walls. If you're looking at two different construction types in your building, you put in your internal walls, your doors, external, internal, windows, your ground floor, any internal floors that you've got, and any other kind of miscellaneous structures or foundations material that you've left out before. So pretty obvious stuff. You've obviously got to put in the materials that are likely to go into the building. For all of these, you've got a drop-down list here. And what I would say, and this is really important because you can use this calculator at a very, very, light touch. You haven't got to do an entire building. But the list that we've got here, generally speaking, is arranged in lowest to highest embodied carbon. So at the top here, you've got sheep's wool insulation. That comes out fantastically low in embodied carbon. And as you work down, you've got wood and clay and concrete and steel, and then you get into the metals. So as a general rule, the higher you are up in this selection table, the lower the carbon. So you choose your material, you put in your thicknesses. And what's worth mentioning here is that this calculator uses, most of the calculation is done through, a building is based on sheet material built up for walls and roofs and things. So, you may have a layer of tiles, you may have a layer of insulation, you may have a layer of plywood, you may have a layer of bricks, concrete, whatever. And so what you're doing here is putting in the thickness of that element. So for our case study, and I'll give you an example here, let's say they had clay tiles on the roof. So you pick clay tiles, and maybe just for argument's sake, those are 10 millimeters thick. So your thickness here are in meters, and you put in your roof area, okay? So for this particular build, it was 320 square meters. Now, don't worry about this divided by 0 at the minute. For every element that you put in, you end up with the actual embodied carbon for that particular element. So immediately you can spot which are the lower value elements, which are the higher ones. So which are the worst, maybe worst performing ones that you want to improve. And the other key thing here is you immediately get feedback on the U value. So for example, if we put in the roof construction for the case study that we're looking at, it had clay tiles on the roof. It had it had battens, but we'll come to that. It actually then had a plywood layer. So you would go down here to keep going. Let's say it's hardwood plywood, and that's 18 mils. You put in 18 millimeters. It then had, what have we got? Because it was a SIPS panel roof, this particular one, you're going to have to build up the SIPS panel. So for example, it had OSB, so it had OSB board with PIR. So there's PIR insulation in there, and then OSB again. So that's your SIPS panel. So pretty simple stuff. And in this particular case, let's for example say it was 18 millimeters, it was 200 millimeter thick PIR, and 0.18 OSB. So that's your SIPS panel construction. And then you've got, say, so it was a warm roof, so you've got plasterboard on the inside, and that is 12.5 millimeters thick. So you can see here that the just the U value hasn't. Sorry, apologies. Right. Let's do that again. Apologies, folks. Just spotted something which I was doing prior to the presentation, which has meant that it's wiped out the U-value calculation. Right, okay, right, we're going to have to deal with that. Let's work around that problem. So, what I was going to say, if I share this again, believe me when I tell you, believe me when I tell you in the version that you download. So you should be able to see the calculator again there, yeah? Rhiannon, can you just confirm that that's showing the calculator okay?
Yeah, you're sharing the calculator.
Yeah. So I say apologies, I was messing around with this calculator before the talk. What we should see here, and luckily I'm not demonstrating for Apple here, the U value here will immediately update. So as you add in these thicknesses for the materials, the U value will update. And as I say, I promise you on the one that you download, that will work. So the U value instantaneously updates, so you can get immediate feedback on what your U value is. Now, one of the bits of feedback that we got when we did this in the first instance was, well, not everything comes in sheet form. You may have rafters, you may have battens, those kind of things. So how do we build that in? If you really want an accurate result on embodied carbon, what do we do? So we've added in for these sections, non-sheet materials. So for example, if we had battens on this roof that the clay tiles were on, you go down here and choose, say, softwood battens. Now, when you're doing non-sheet materials, you have to put in thicknesses, width, and pitch. Okay, so the thickness, we're talking about the depth into the roof. So for example, if these were 25 mil thick battens and they were 32 millimeters wide, and the pitch, say they were on 200 millimeter centers, that gives you that's all the information that you need to put in, but you do need to put in the roof area again. For various reasons, we had to split out the roof area. So if you have joists, you could do the same thing. If you had battens in this particular case, you can see that. And again, it updates it and works out the right value. Now, the reason you won't get any values in this cell here until you fill in floor areas. And this is really important to remember, that embodied carbon is that the metric that is used is per square meter of floor area. So in this particular case, the total floor area was around about 280. So the ground floor was 190, and then upstairs was 90 as well. So these bright yellow cells down here are really important because these are the floor area. So if you want some meaningful results further on in the calculator, then you must fill these bright yellow cells in with the total floor area. So that's ground floor and then any internal floors. So once we've filled that in, lo and behold, we've got a value here for the roof construction. Okay, and you can put in notes here. You know, you can type whatever you want in the notes section to make whatever notes you want against that particular construction. So all being well, you can then kind of move on to your next section. As say, the U value will be right as well. So external walls, for example, you just do exactly the same thing. So for example, let's say, for example, this particular one had timber cladding in here somewhere. So say we've got timber cladding, then say that's on battens again. In fact, what we'll do, we'll put the battens in the non-sheet materials section. So battens, we've got battens in there. I mean, I tend to find it's useful just kind of building up the construction, then putting the thicknesses in. In this particular case, for this house, it would have had plywood on the outside. So we go down and find plywood. I chose a softwood ply there, but it could be hardwood plywood. We've got uber thick walls, and again, because this was a SIPS construction, this was PIR again. So again, not particularly that great on embodied carbon, but this is what it was. And then on the inside, you might have OSB. And to say here that you've got a choice of about 45 materials. So there's plenty to choose from. Of course, we haven't got every material in there. We've left out things like membranes and Tyvek and things like that. These are the more kind of juicier construction materials. And then there would have been an air gap. So in this particular one, in this particular construction, there were a couple of battens. There was battens on the outside of the house and battens on the inside of the house, and then there was plasterboard on the inside as well. So it's put in the plasterboard. So the timber cladding, say the timber cladding was 10 millimeters thick, the plywood was 18 on the outside, the PIR was 0.2 of a meter, the OSB was 0.08. And the plasterboard was 12 millimeters thick. Again, you can kind of see where I'm coming at here. It's pretty straightforward. An important note here, we've got a couple of important notes. For the walls, for the external walls, we are not including for the windows. So you must make sure that you leave the windows out of it, out of the areas, because we're adding windows in further on down. So what you don't want to do is double up on materials. The battens, again, for example, these would have been 25 millimeter thick battens, and their width would have been, say, 0.032. And their pitch, on the outside of the roof, they might have been tighter. On the inside, they may have been less. So, you know, again, we can put in some relevant numbers here. And remember, you have to put in the wall area over which that covers. We appreciate that you may have battens over a particular wall area that isn't the entire wall area. So you can put in different values there, and that will take that into account. So we've done the roof, we've done the external walls there. The internal walls, same thing again. So we haven't got U values for internal elements because it is meaningless. But the walls, for example, you know, for say for a standard building, you might have plasterboard. You may have, let's say, for example, you may be putting acoustic insulation in there. You may be putting joists in there, and of course you probably have plasterboard on the other side. In this particular case, it's entirely up to you, depending on the level of detail that you want here. You could, for example, for stud walls, use the non-sheet materials bit here. So for example, if you've got studs with insulation in between, what you could do in the non-sheet materials bit is put in acoustic insulation and your softwood joists. And I'll show you how to use this bit. The plasterboard, for example, because you've got two sheets, you can simply add that thickness up together. So rather than being 0.125, you could have 0.025, it does the same job. And the area of the internal walls in this particular example, I think was around 120 square meters. So to do your internal walls here, and again, this is just to pick up on where you've got non-sheet materials, say the wall thickness is 0.1 meters thick, pretty standard. The width of the element, so the acoustic installation, imagine you've got 400 millimeter pitch joists in there. When you add these two together, if the pitch is 400, these two cells have to equal 0.4. So for example, the acoustic insulation may have been 350, and then you've got 50 millimeters for the joist. So together these are equaling 0.4, and the pitch for both of these is 0.4. So again, you know, you can go as accurate as you want to this, and because all the internal walls are joisted or have those studs, we've got to put in that wall area again. And again, you can see here, you start getting a feel for the embodied carbon. So for the internal walls, if you're using wood and acoustic insulation, you're down at some pretty low numbers, 2.6, whereas, you know, the external walls are up at 54, the roof's up at 77. And although we'll go through the rest of this, you can see at any point here, you can scroll down to the bottom, see where you are against your domestic RIBA targets, and see against the various clusters that we've got here, relatively, you know, where the embodied carbon's coming in. So we've done the internal walls there. The external doors. Now, this is really important because, you know, there are many different external door types as there are at probably days of the year. So we've had to go kind of sensible here, and we've just assumed a kind of middling value for embodied carbon for doors. The other thing that you've got to bear in mind here is that doors as an area of a building are fractional. So don't get hung up about, oh well, I may be using, you know, wood harvested from the garden versus UPVC doors, you know, brought in from America. There are other materials in the building which will have a far bigger impact. So let's say there are two external doors on this building. Of course, if you've got big glazed doors and things like that, treat them as windows. But if we're kind of talking about standard doors, think about doors in that context. And the internal doors, let's just say there were 10 internal doors for this particular building. And those are assumed to be, kind of softwood, kind of again, middle of the range doors. The windows, we've just gone for double and triple here. Hopefully none of you are designing buildings with single glazing anymore. So we've got double and triple. And again, we've gone for a kind of a middling embodied carbon value based on materials for double and triple. We have made a slight choice between wood frame only and wood and aluminium frame for triple glazing. And then we've got double glazing, which is just kind of middle of the range wood and aluminium frame. So you can pick either of those. For this particular case study, they went for half decent triple glazing, and they had about 73 square meters of glazing. Okay, so again, you can see your total embodied carbon value there and your embodied carbon per square meter of floor. So the ground floor you're looking at, you can treat this really as you like, for slab buildings, you can obviously put it in here. If you've got footings, you can put that further down the bottom. These all get added up together. So as long as it's covered somewhere, then you're okay. So we've got a difference here. So the ground floor, again, we've got a U-value calculation, which in this particular case won't update, as described before. And internal floors, you might have mezzanine floors, you may just have bog standard internal floors, and you can build all this up. So for this particular case study, this had a raft, this had a kind of a concrete raft, actually a reinforced concrete raft for it. So you had hardcore, you had EPS insulation in there, and we had a concrete raft. So you have to go quite far down for reinforced concrete. We've got recycled concrete in there, we've got poured concrete, we've got concrete blocks, and then right down here is still rebar reinforced concrete. Now again, we've made an assumption here about, say 6mm rebar on like 200 centers. If you really wanted to go into detail here, you could put in bog standard concrete, and then at the bottom, you can drop in, under this miscellaneous section, steel. And if you want to work out, exactly the amount of volume of rebar that's going into the footings, you can do that. Otherwise, you can just pick steel rebar reinforced concrete and get a pretty decent value here. So the hardcore in this particular case was about 0.2 of a meter thick. They had a whole load of EPS insulation at about 300mm thick. And the raft actually was around about 125mm thick as a general rule. So you can see here immediately the impact that concrete's having on this line here, 44 tons of embodied carbon there, just for that floor slab, and steel adds a massive amount to that figure. If you compared that to, say, just a concrete slab, you go down here, say use recycled concrete instead, and put in 125, and look, that's dropped from 44,000 to 6,000. So again, you get real-time feedback on relatively what these materials are like. So if we take those figures out anyway. Internal floors, again, you can build up the internal floors. It may be that you've got acoustic insulation in there. And again, you don't have to do this in any particular value. You may have, let's say you've got hardwood floorboards, for example, upstairs. So, sorry, where are we? We're getting lost here. So say we've got, maybe you've got hardwood plywood, for example, upstairs. You haven't got carpets and things and stuff like that. But again, this gives you an idea. Maybe you've got 200mm of acoustic insulation in the floor. You've got plasterboard on the ceiling of the floor below. So we put in some plasterboard. 125. Okay. And you just punch through, getting the idea. So it can be fairly monotonous. And when you then get to miscellaneous structures, often these are kind of reinforcing things. So we've got steel in there, we've got wood, we've got concrete. There's not a massive amount of choice here because usually reinforcement comes down to those things. So again, you can pick, you can work out volumes, you can put in thicknesses, widths, pitch if it's rebar and stuff like that. And then in foundations, again, you could work out how many cubic yards. Maybe you've got a pet QS that's giving you, or a structural engineer that says, well, you know, put in roughly this. You can put in again, you know, volumes of bricks or concrete, and other things that you may put in footings. And it's important to understand that this is volumetric now. So you're putting in, say you had 2 cement mixers of concrete, that might be 12 cube or 12 cubic meters of concrete. So if you pick concrete, you'd be putting 12 in here, okay, as a volume, and immediately you would get that feedback. In this particular case, you don't need to do that. Just have a raw foundation. So you've put in all your key kind of building fabric elements. Now we're on to the technologies. We're on the kind of the final stretch now. So you can choose whether you're going to put solar PV on your building. Now, this is where it is really handy to reference this operational energy target table again. So for example, if you're trying to pitch at a 2030 building, you know, you're going to need to be looking at air source or ground source and underfloor heating, mechanical ventilation, heat recovery, and around about the 4 kilowatt mark as a number for solar. In this particular case, this project actually did have 4 kilowatts of PV on the roof. To put that in. Now you've got 2 options here. Some people understand kilowatt peak of solar and others don't. So we've got 2 options here. You can either put in the kilowatt peak in this kind of quantity column, or you can put in the square meterage of solar that you're putting on. Now, to be sure here, it will pick up both of these values, but if you have a preference, make sure the other cell is 0, okay? And in this particular case, we're going to be happy with 4 kilowatt peak that we put in there, being able to pick up the solar. These values will come out fairly high for embodied carbon, you know, and you'll get an appreciation for that. Certainly solar PV, all of this assumes that the building lasts for 60 years and your solar PV system will be changed at least once during that term. So all of that, those extra costs are built in. Certainly embodied carbon impact is built in. You can choose from a heating system. So you've got air source, ground source, gas boiler. In this particular case, the guy had an air source heat pump in. You can choose between underfloor heating and radiators. Again, actually, there's not that much difference, surprisingly. If we choose radiators here, you can see it's 8,000. If you choose underfloor heating, it's only fractionally more. So, you know, again, don't get mega lost in the detail here. This is just to give you an initial indication. And again, you can pick from mechanical ventilation only or mechanical ventilation and heat recovery. Now, in this particular case, this building's done okay. You're at 242 here. So this total here is your total CO2 per square meter. You're within the RIBA 2030 target. And you can see here that, you know, you've got these relative bars that are showing you how that compares. Now, at the moment, if you want to do another building or another comparison run, you've got to put that information in again. You know, we are looking at ways that we can get that copied over, and that may be for the next version. But as I say, I think that's enough for the moment to kind of give you an idea. There is some repetition in here, and once you get the idea, it's pretty, you know, it's pretty straightforward. So I will leave the demo for there for now, and we'll take a look at some questions. So if I let's just see if we can bring up the chat here. Rihanna, have we got any questions then?
Yes, we have quite a few.
So I'm trying to find my chat box so I can actually read them.
From Charles, does that comparison capability run as far as being able to run full scenario comparisons?
Just trying to think what you mean there, Charles. I mean, you can of course, you know, put in as much detail as you desire on volumes and wall areas and constructions and things. It obviously has its limits because of the amount of materials that we've got here, and none of this, you know, completely replaces a proper you know, LCA assessment of a building, but this is to get you along the right lines. And we believe, though we don't.
I think you answered the question at the end of your presentation by saying that you hadn't got the replicant function on it yet. What I was really asking is, could you sort of run scenario A and then sort of fiddle around with it and maybe change, for example, one of the construction elements, and then see what effect that was having alongside it?
Yeah. I mean, you can at any stage here. I mean, this kind of live update. So it's not like you're filling in the information and then you're pressing run, do the calculation. This is all just live updating. So, for example, if you decided that you didn't want a SIPS construction here and you wanted hempcrete, you could put in hempcrete. Just change one of these drop-down boxes, and it will update the U value. And those other values instantaneously. So you can choose to do that on one particular building type, or you can duplicate the values into another one of these, kind of parallel, building design boxes that we've got next door. But it's kind of real-time update based on the data that you're putting into the spreadsheet.
Okay, next one from Owen. Do the indicative target U values apply for both domestic and non-domestic projects?
Yeah, the U values are just U values. So this table that we've got here are the domestic ones. Now, of course, we get involved in commercial projects as well, and it would be helpful, no doubt, if we could have a commercial equivalent of this, and that's something which we will be working on, because I don't necessarily think that the U values will change massively, but certainly the targets for embodied carbon are completely different for a domestic premises. So yeah, we'll be looking at how you can switch between domestic and commercial. It may be the case in the next version that up the top here, you can pick from domestic or commercial, and of course it updates the at the bottom here, it updates your targets and where you sit against the commercial targets as well. So as with all these things, we're always welcome for comments, and the most popular ones get changed first, like any kind of software or program update. So in summary, Owen, this is a domestic calculator at the moment, but the commercial targets and calculator will probably be the next logical step on from this.
Next question from William. Are you limited to only 2 types of each? Do you have different options for different lambda values for different types of installation, or is it a standard assumption to be used as a benchmark later in the project?
Yeah, essentially, yeah. So for every one of these materials, we have assumed a mid-range thermal conductivity value, which is a lambda value, which then comes out to U value. So again, none of this replaces a proper U value calculation, but we think it's pretty close. I mean, you have got materials, for example, I added here the other day, we've got some pretty good alternative materials here. If we just have a look at walls, I'll give you an example. We've got clay, we've got straw bales in there, we've got hempcrete, we've got adobe. Say adobe, for example, which is a kind of a clay brick material. There is a variation on the lambda values and stuff for that. So again, we've picked a mid-range value, but invariably, depending on the final type that you choose and the final makeup of that, then that lambda value may well be different. So yeah, this is very much indicative, and I would stress again that this is lifting the box and giving you guys generally a hell of a lot of information that you never had before, but none of this replaces kind of proper final analysis to make sure that you get across the line. This is why we call it a stage 1 concept calculator, not a stage 4 detailed design be all and end all calculator.
Another question from Charles. What if you are using bespoke size doors? Do you use standard door size equivalents, e.g. double size equals 2 doors?
Yeah, basically, yeah. I mean, that's a really good question. So we've used standard, 800 wide by, 2 meter high doors. So if you make that assumption and you've got doors which are 1.6 meters wide by 2 meters tall, then assume that you've got twice as many doors. As I say, if they're glazed, internal doors you would double up. External doors, as I say, if they're heavily glazed, then treat them as windows. Again, don't get too lost in the detail. The door area compared to wall, roof, floor areas make the figures pretty trivial, really. I mean, to give you an example, looking at the doors on this example that we've done, 0.1 is the 0.1 of a kilogram per square meter, and your overall value is 242. So, point whatever that is, 0.03%, or 0.3%, should I say, is what the doors add up to. So as I say, don't get mega lost in the detail. But yes, standard door sizes are assumed when you're putting in doors.
Next one, do not understand what pitch is measured in meters.
Okay, so really quick one. For example, if you have, let's take our example here on the walls. So whatever it is, essentially, if you've got battens on a roof, so if you had say you had rafters on a roof, you've got your weatherproof membrane on, you put your battens on the roof, the pitch of the battens is the distance between those. So for example, if they're 200 millimeters apart, that's the pitch. So the battens themselves may be 25 millimeters thick or deep, should I say, by 0.032 of a meter, or 32 millimeters wide. So that's the sectional area of your batten. And then those battens are every 200 millimeters up the roof. So the pitch in this particular case is 0.2. If you've got studs in a wall, they might be on 400 millimeter centers, or 0.4. So the pitch for those is 0.4 of a meter. Again, it's just a way of getting away from elemental kind of thickness build-up to something that's, not sheet material. It's actually got a depth and a thickness, and happens every so often, and that frequency is your pitch. So it's the distance between things is your pitch.
Okay, question from Rishab. Very interesting to see the carbon reduction 85% from the reinforced steel concrete, which is more common compared to recycled concrete. Is there a major cost trade-off to make the move to the recycled technology?
That's a good question. You get to see that in the kind of the proper one-click LCA software, in this kind of professional software. That is invariably there will be an uplift because there's additional processing there. But I couldn't tell you exactly what the uplift would be. I'd be lying if I said, oh yeah, it's 50% more or it's 5% more. I simply don't know what that uplift would be. But that is something else which, again, you've got to balance in all of this. It's fine throwing these amazing low carbon materials at the project, but you have got to keep an idea on cost as well. And certainly for this doesn't focus on cost, because there's loads of variables about being able to source stuff from down the road versus being able to source the stuff from the Midlands versus the States versus Denmark. And what I would say in that regard is what we haven't included here is transportation costs that add to the embodied carbon. So you could, in theory, you could build a low embodied carbon home, but bring all your materials in from, Malaysia, and that's obviously going to add to your embodied carbon. Alternatively, you could build a low embodied carbon building and source all your materials from a 10-mile radius, and of course that's going to save you quite an amount. So you have got to use your common sense and make sure that you do bear in mind that this calculator certainly assumes that materials are sourced within a kind of a sensible distance away from site, and that you might want to come in a bit under to make sure that when you add in those transportation costs, embodied carbon wise, that you're not going to be going over the targets.
Okay, next one from David. What if you have a framed building, steel, oak, say?
So really simple. So we can, so the way that you would use this, for example, say had an oak frame building, is you would, let's have a look at the roof, for example. Say you had, trusses or something like that. That is going to take a bit more work, in as much as you're going to have to work out what the volume of that oak is. For example, I mean, maybe you've got, I don't know, 150 by 150 section oak beams which are running up the roof. You can treat that like a roof joist. So for example, you could choose wood in here somewhere. Although I think it's a generic wood if I've got it right. We do have wood in here. If we don't, we'll certainly add it in. But yeah, if you've got an oak frame building, you would choose wood in the materials section. You would give the thickness of, you would give the thickness of that material, and you would put it in this non-material sheet materials section. So you put in the thickness, the width, and the pitch, and just treat it like a joist. And then you would say what area that covers, and it would take into consideration the embodied carbon in that. So let's say you had dropped wood in. Let's say for example we just drop in say hardwood plywood for the minute. The thickness, say it's 150 mil thick, it's 150 mil wide, and the pitch, I don't know, let's just say every meter, and the area over which that covers is, I don't know, next 200 square meters of roof. So you would treat it like a joist. That is probably the most effective way of doing it. The other way you could do it is, if I've got this right, so in this miscellaneous section, you could drop in wood here, for example, and drop it in there if you didn't want to put it in the roof. I don't think it makes much sense. I don't think we've got wood as an option down in foundations. Otherwise, you could kind of work out a volume. But the best way to do it would be to treat those oak beams as essentially joists, and you just put in bigger dimensions and the appropriate pitch for those. It's all volumetric. So all that we're doing here, to give you guys an insight, is thickness times width times pitch is kind of essentially telling you the volume of that material in a given square meter. So depending on how good you are with maths, you can make slight adjustments in these figures to cover that off. But I would say, as a starter for 10, just treat it like a joist, big, thick joist.
Okay, next one. Can the user import a unique material or material library?
No, not at the minute. Again, that was another consideration we had, whether you could put in bespoke materials into the mix. That's certainly something which, of course, would suit some people. Assuming you've got reliable information for the embodied carbon, kilograms of CO2 for the lifetime of the material, and these are whole life cycle figures. So if you can get reliable data for that, then of course you can throw in individual materials, but you can't at the moment. And that's a fair question, because I could see that could be useful for people going forward. So by all means, we'll log that as a potential thing to do. But it had crossed my mind that might be handy for the next version.
So, question from Charles: is this calculator purely for white box, or can you incorporate kitchens, bathrooms, etc., even if it is on an assumed value per area covered basis?
Yeah, so we haven't done kind of internal fit outs and stuff added to that. What we have done in the background, we have added a notional value for plumbing, but what we haven't done is put in values for kitchens and toilets and stuff like that. When you're looking at the embodied carbon of a building, generally speaking, those kind of fittings within a building don't form part of the calculation. But it's something we'll certainly consider, and if we think it kind of makes sense to do that, then we can give you that option. Of course, it could be using porcelain this or wood that, and that would obviously add to the embodied carbon. But generally speaking, that doesn't form a kind of a key part of the calculation, so it's not included. But we have got a background value for replacement of windows and doors and plumbing in there that isn't shown.
questions are racking up. I mean, obviously we'll just keep going through as much as we can.
Yeah, we'll do another few minutes, and unfortunately we can't answer all of them.
No, and if we can't, obviously we'll get back to you. But
yeah,
do rafters, battens, etc. include for fixings which could be significant in a timber frame building?
they don't. Again, you know, there's an opportunity to. It really depends on the detail you want to get to. To keep this simple, we've just gone for the embodied carbon for a volume of that pure material, and you can add this in. If you want to go to the level of fixings, then by all means, you know, you can drop in. If you've got, I don't know, steel screws that you want to put in there, you can put in, you know, I don't know, say virgin steel. You can work out, you know, what the volume is, or the thickness, or the relative, you know, pitch of fixings that you're putting in, and drop those in. I can promise you that cost benefit wise, as in cost as in your time and the actual benefit that you'll get out with the adjustments in the figures, it's going to be pretty negligible. The great thing is you can try it and see how negligible it is. But the best thing to do would be able to pick the closest material in this kind of miscellaneous other structures bit and drop that in. So no, we haven't included the fixings and stuff like that. You know, where they may be more common, you know, for particular construction types.
Question from Lisa. Could you have different types of internal walls, i.e. if you were doing a flat development and wanted party walls, partitions and
yeah, that's right. Yeah, so I've just scrolled to this section here. So absolutely, we've got two different types of internal. Oh no, that's floor. Sorry, apologies. Internal walls. Where are we? So you can do, and again, you know, there's nothing magical going on here. What you could do, for example, we have actually only got one internal wall section, but for example, if you can keep it tight, you could have. At the moment, we've got a build up here for like a stud wall. But if, for example, if you had another wall construction, you could continue to drop materials in. So although you've got two wall constructions, you can you could drop them in. You could drop them into this section and adjust your areas appropriately to make sure that it was a kind of a balance between the two. If you're really lucky, those wall areas may be identical. It's highly unlikely that they will be. But at the moment, we've only got one internal walls section within the calculator. So I would suggest you drop the materials in. And if you're at all unsure, you could always change this to 1 and then obviously multiply these figures, you know, the various figures against, you know, the embodied carbon that comes up from that particular wall construction. But it's something again that we can add if there's enough demand for it going forward, a second internal wall construction.
Yeah, we had a question from Jeremy, but I think you might have answered it already, Doug. Would be interesting to know what it assumes for finishing, fittings and sanitary ware.
So nothing, essentially. I mean, we've dropped plumbing in there in the background, but there's nothing for kind of sanitary ware and that kind of stuff.
Question from materials to you derive embodied carbon figures from specific manufacturers' EPDs? Yeah,
absolutely. So this one-click LCA software, I think that draws upon, I've heard mixed figures between about 9,000 and 12,000 EPDs, which are, if you're not familiar with an EPD, it's an environmental product declaration, which is a third-party verified embodied carbon calculation for a particular material. There are lots of standards around the world, but it's a kind of a universal standard against which these figures are drawn from. And one-click LCA, that's all they give you. If it hasn't got an EPD, it doesn't make the software. And we've used all those values in this calculator, well, certainly for the materials listed. So yes, they do come from proper accredited EPDs that can be relied upon.
Okay, question from Margaret. Could this be used for retrofit, and would the calculator then give credit for existing fabric reused? This could help clients decide about renovations via new builds.
Yeah, that's a tricky one. I mean, certainly when it comes to refurb, it's always a bit sticky as to what target you try to meet when you've got an existing building already there. Of course, if you're building a new bit to that building, then the new bit could meet the new standard. You could argue for the existing materials already on site that there is no additional embodied carbon. So unfortunately, it's a bit of a grey area. I can't give you a crystal clear answer, but that question is coming up more and more. And when we get more clarity on it, we can try and impart that. But it is tricky. I mean, in most cases, new bits of construction, I would try and look at the target for existing buildings. Maybe that you're refurbing, of course, you can have a look at the embodied carbon of the bits that you're adding. Maybe you're improving the insulation or adding things onto the building. Onto existing structure, but for the existing structure there, you could argue that whilst it is material that's there on site already, it's either got no embodied carbon or it's embodied carbon that's, you know, well outside of its 60-year lifespan, and so doesn't need to be included in the calculation. But sorry, I can't give you a clearer answer on that. Okay, Rhian, we'll take one more. I think it's probably best to wrap it up.
Okay, last one from Seb. Is this representing RIC's modules A to C, or does it also include sequestration, assuming responsible end-of-life processing for the timber used? Say that all in one breath.
Yeah, so my understanding is, yes, it covers it. This uses covers the RIC's phases from A to C, but doesn't include sequestered energy from timber in particular. So again, that's something that we can get clarified by one of our guys at our end. But as far as I'm aware, it doesn't. Okay.
Okay.
Right.
Any questions we haven't answered, then obviously we can pick up. There's only a couple more. But I think they're quite in depth by the looks of it.
Okay, great.